Hello and welcome to the AICE Chemistry lecture series. Today we're going to look at chapter 6, section 6, which focuses on calculating enthalpy changes using bond energies. So we're going to expand on the idea of bond energies that we saw in section 5. So if you have not seen the section 5 video on bond energies, I would highly recommend you pause and you go back and watch that video before you watch this one. Now, just like with enthalpy changes, we can do Hess cycles with bond energies. And that's mainly what we're going to look at today. So, we can actually find the standard enthalpy of a reaction by using the idea of bond energies and a Hess cycle. In this cycle, we use the atoms in the element as the gases intermediates. So, we're going to start with drawing our regular Hess cycle with our reaction at the top, so reactants yielding products, and that's the enthalpy change of reaction that we are drawing up here. And so that enthalpy change of reaction, the reactants yielding the products, is going to be what we're trying to find. Now, with using bond energies, whenever we break down bonds, what we are going to create as an intermediate is the gaseous elements. The gaseous elemental atoms. So not the elements in their elemental form, like enthalpy change of formation, you have to be very careful about that, but the atoms, individual atoms in the gas state for those elements. So whenever we have something like the reactants, whether it's CH4, CO2, any compound, we can break down that compound or those compounds, if it's multiple, into gaseous elemental atoms by using the enthalpy or the bond energies for the reactant bonds. Now that does mean that we need to have a very clear idea of what the Lewis structure for that reactant looks like, because we need to know every single bond that's in it. But essentially, the process of going from the reactants to the individual gaseous elements, that is the enthalpy of the bond, or what we call the bond energy or bond enthalpy. We can do the same with the products. Now notice that both these arrows are pointing down. Why are these arrows pointing down? Because when we talk about bond energies, we're talking about the breaking of bonds, not the formation. Remember, bond energies are always positive because we're talking about bond breaking. So we're going to go from the reactants to the atoms because we're breaking the bonds in the reactants and forming the gaseous atoms. And then the same thing for the products. We're going from the products to the gaseous atoms. And those are the arrows that represent the bond energy for both the reactants and the products. From there, it's the same as we saw in Hess cycles in a previous section. All we need to do is look at the alternate path. So we find the two arrows that agree in direction, in this case as the purple and red arrows, and that's our alternate path. Which means that the enthalpy change of reaction plus the bond enthalpies or bond energy for the products added together are going to be equal to the bond energies of the reactants. Or if we rearrange this to isolate the enthalpy change of reaction, enthalpy change of reactions is equal to the bond energies of the reactants minus the bond energies of the products. And so again, most of the time you will not actually need to draw out the Hess cycle. Maybe 10% of the questions will ever ask you to actually do that. But using this equation is very useful. Is very useful for the mathematics. The enthalpy change of the reaction is equal to the bond energy of the reactants minus the bond energy of the products. Now, let's take a pause here because you could just memorize this equation. But let's think about what it actually means, because then things make a lot more sense and they're easier to remember when we actually understand them, right? So why is it reactant bond energy minus product bond energy? What are we doing to those two things? Well, we need to remember a couple things. First of all, bond energies are for breaking. Remember, by the definition, the bond energy is the amount of energy needed to break the bonds in a compound. That's why they're always positive. So let's think about what we do with the reactants and the products. Well, for the products, we're always forming the bonds, right? Because we're creating the products in a reaction. So we're always creating bonds. Whereas for a reactant, on the other hand, we're always breaking bonds. So that is the first thing we need to understand, right? When we are either looking at the bonds, for the reactants, we're breaking apart the reactants, breaking their bonds apart to create the gaseous elements, and then from the gaseous element create the products. That's what the reaction is. Breaking the bonds in the reactants, creating bonds in the products. So the units, the signs here make sense, because if you notice, we have the bond energy for the reactant bonds. Well, we break reactant bonds. And since bond energy is bond breaking, it's always going to be positive. We keep this one positive because the reactants match the definition of bond energies. It's a breaking of bonds. On the other hand, the products are being formed. This does not match bond energies, right? When we talk about bond energies being positive, that's because they're always for the for the breaking of bonds. Since the product bonds are being formed, not broken, that's why we have this negative in front of the enthalpy or bond energy for the products, because we're forming those bonds. Therefore, it's the opposite of bond energies. So the negative bond energy is equal to bond formation. That's why we have the negative bond energy of the products, because the products are being formed, but the positive bond energy of the reactants because the reactants are being broken, the bonds are being broken. So now that we understand that, let's look at a practical application. Let's look at an actual paper 2 question. Using equation 1, which is right here, 2HI yields H2 gas plus I2 gas. And don't worry about this. This is a yield arrow. It's called equilibrium arrow. We will look at that in the equilibrium chapter. But for now, just picture it as a regular reaction. Use equation 1 and the bond energy values in table 3.1, so they give us bond energies, to calculate the change in enthalpy delta H for the thermal decomposition of 1 mole of HI. Show your working. So they're asking us to show the enthalpy change for the thermal decomposition of 1 mole of HI, which essentially just means show the enthalpy change of the reaction. So how can we make a Hess cycle here? Well, the Hess cycle here will be that 2HI can form H2 plus I2. That's our reaction that our question was giving us, right? So we have those hydrogen iodides being turned into individual hydrogen and iodine molecules. Well, how can we create a Hess cycle that uses bond energies? Because what we are given here in the question are bond energies. So we're being asked for delta H here. We're being asked for delta H of reaction, and we're given energies, bond energies. We'll put X here because we don't know there's different bonds, but we're given bond energies. So because we're being asked for delta H and we're given bond energies, we need to do a Hess cycle that uses bond energy. So anytime we do a Hess cycle for bond energies, we put our reaction at the top like we normally do. And then at the bottom, we're going to put the elements in their gaseous state as atoms, not their elemental force. So notice, I have hydrogen and I have iodine. I didn't put H2 gas here. I just put H gas. Because for bond enthalpies or bond energies, we're going to put the atoms of the elements in the gas state. And then I don't put I2, I put I. In the gas state, even though iodine I2 is usually a solid in the elemental form, we're going to put I gas, because again, it's the atom in the gas state. We have 2 hydrogens and 2 iodides. So if we look down here, if we grab HI and create 2H and 2I, what we're doing is that we're breaking 2 HI bonds, because why 2? We have 2 HI. HI is just simply a single, actually let's do this in green, it's just a single bond between hydrogen and iodine. So we have 2HI representing HI, and this has lone pairs, even though they're not really relevant right now, and HI. So when we look at making from 2HI, 2 hydrogen and 2 iodine atoms, what we are looking at here is essentially the breakage of these HI bonds. And there are 2 of them because there are 2 molecules. So what is this equal to, the 2HI to 2H and 2I? It is 2 times the bond energy of the HI bond, the amount of energy needed to break the HI bond. On the other hand, on this side, we have H2 and I2. Well, H2 is 2 hydrogen atoms bonded with a single bond. So we have H, H. And then I2 is 2 iodine atoms bonded with a single bond. So if we're breaking apart this H2 and this I2 to create 2H and 2I, what are we going to need here as far as energy, bond energies? We're going to need the bond energy of the HH bond and the bond energy of the II bond. Why? Because when we look at breaking this, we're breaking the HH bond in the H2 molecule, and we're breaking one II bond in the I2 molecule. So it's a bond energy for HH plus the bond energy for II. Once we have all of that, once we have the specifics, again, we have the reaction at the top, the atoms in the gaseous state at the bottom, then the arrows point down because these are bond energies. We can find our alternate path arrow, which means that delta HR plus the bond energy of hydrogen bond, plus the bond energy of iodine bond is equal to 2 times the bond energy of the HI bond. If we want to find delta HR, all we have to do is rearrange this, subtract the bond energies of the products from both sides, and we get the delta H of R. This shouldn't be F, should be R. Delta HR is equal to 2EHI minus EHH minus EII, E being the bond energies of those. And then if we bring in our bond energies from our chart earlier in the question, we know that the HI bond energy is 299. We know that the bond energy of HH is 436. And we know the bond energy of II is 151. So 2 times 299 minus 436 minus 151 gives us that the enthalpy change of reaction, again these are F's but it should be R's, is going to be equal to negative 11 kilojoules per mole. Now again, this makes sense. Notice, HI is the bond in a reactant. HH is a bond in a product. HII is a bond in a product. Notice how the products are both negatives. Why? Because we're forming those 2 bonds. And those 2 bonds are therefore negative because bond energy is for breaking bonds. So if we want to make it for forming bonds for products, we make them negative. So this is the enthalpy or Hess cycle approach to solve this question. If you wanted to, you could simply just remember the equation we talked about earlier. Delta HR is equal to the bond energy of the reactants minus the bond energy of the products. And you can see here, reactants, HI, bond energy, minus the product, minus the product. Again, always keeping in mind that if there is a certain number of bonds, right, like there are 2 bonds here, we need to carry over that number into our calculations. All right. Now, there is one more thing we have to look at. I'm going to hide this real quick, and I'm going to go back to the question. So what we found here is delta HR for the reaction that we have here. However, notice that in the question it asks for the thermal decomposition of 1 mole of HI. What we found is for the reaction here, which is a thermal decomposition of 2 moles of HI. So we have to be careful when answering Cambridge questions of the specific things that they're asking us for. Because they're asking for 1 mole, there is one more thing we need to do. bring this back up. So here we found the enthalpy change of the reaction, but the reaction is for 2 moles of HI, not 1. And this is where Cambridge will have you actually have to think, right? Use some critical thinking. If this is the enthalpy change of the reaction as it's written here, and that is for 2 moles of HI, then since the question asked us for the enthalpy change of reaction for 1 mole of HI, we need to divide by 2. Because this is for 2 moles of HI, not 1. And the question wanted it for 1. Meaning the answer to the question, not delta H of this reaction, but the answer to the question is 5.5 kilojoules, negative 5.5 kilojoules per mole. Or negative 11 divided by 2. And again, that comes all to the wording in the question. This is just a reminder. Be very careful with the wording in these questions. Because the question asks not for both moles of hydrogen iodide. So the enthalpy change of this reaction, because the enthalpy change of reaction is as the reaction is written, because the question is asking us for the thermal decomposition of 1 mole of HI, not both moles of HI in the reaction, then we need to, when we get our final answer, which is for the 2 moles of the reaction, we need to divide that by 2 to get a negative 5.5. And we could have done this from the beginning. We could have done this as HI yields half H2 plus half I2, and then just put H and I down here. Or we can do the whole thing like normal and then divide by 2 at the end. If the approach is up to you. But the critical thinking aspect is very important. So if we look at our mark scheme here, we can see that what we get the points for. So evaluation to give a value based on calculations using all 3 correct bond energies, correct use of stoichiometry to calculate delta H for 1 mole of HI, meaning that you can do it as changing the coefficients, or you could do it at the end, and then calculate a value for delta H correctly, meaning using the values correctly. So there are 2 points here, and then this is what we would normally look at as a tick, as a dot tick, which for Cambridge, that means how is graded, right? Because you notice there are 3 things here, but there are 2 points. That means that the first of these 3 things that you do gets you a dot, meaning you did it. The second thing gets you a check mark, which is 1 point, and then, or a tick mark. And then the third thing will also get you a tick mark. Meaning that 2 out of these 3 things being done correctly will get you only 1 point. But all 3 of them being done correctly will get you both points. If you only do 1 of these things correctly, let's say you just use all the bond energies, then you wouldn't get any points. But that's it. I mean, this is just a very simple Hess cycle using the same Hess cycle ideas and Hess cycle knowledge from the previous section, but we're doing it here with a new type of enthalpy change, which is bond energy, just the enthalpy change of breaking bonds. That is it for chapter 6. That is it for thermodynamics. It is a very complex chapter, so make sure that you go all over the videos again and make sure that you're keeping in mind to think not just mathematically, don't just do the math, but think logically. Use the theory and the understanding you have of how energy works in reactions to then actually figure out whether your answer makes sense. Is it supposed to be positive? Should it be negative? For example, this is a decomposition reaction. It's thermal decomposition, meaning we're heating this thing up. So it makes sense for our answer to be positive. Whereas if there's a combustion reaction, this will not make sense for it to be positive. So use that kind of knowledge, use that kind of critical thinking to double check. Not necessarily the number itself, because that is going to be harder to do, but the signs in your answers. Well, I'll see you all in the next chapter.